All right, welcome to the last page of the notes. And the thing is, what we have done so far, it can be extended to a more complicated type of region that's shown. And so basically, our thetas are still going to be constants. All right, we're going to go from counterclockwise, so our thetas are still going to be constants. But what if our regions are bounded by actual functions, even though it's a circular path? Our two radiuses are going to be defined by actual functions. And so if that's the case, the only thing that changes is that, our upper and lower bound for our integral is just going to be defined by an actual function, and that's going to be a function, that's defined by theta. So that's all that's saying. All right. Example 6, evaluate the iterated integral by converting to polar coordinates. All right, so the first thing that I want you to do is notice, okay, the outside variable is y. So I have y equals 0 and y equals a. Again, I want to graph the region. I want to see what it looks like. And then secondly, I have going from the region x equals 0 and x equals negative square root of a squared minus y squared. So that tells me something about, where the x is going to be. But that's also helped defined by y equals 0, y equals a. And so I want to solve this over here for x, so we're going to go ahead and do that. So I'm going to bring the x over, then square it. So a negative x squared is just going to be x squared. And then bring that y squared, so it's going to give me x squared plus y squared equals a squared. All right, so now I know what I'm drawing. I have a circle. All right, let's draw the region. I'll stick with purple. All right. And it looks like the radius is going to be defined by a. All right. So our radius is a. So that would be like negative a. And we're told that x equals 0. So it gives me this line too. X equals 0. All right. Then we have y equals 0. So y equals 0. All right, and y equals a. So this is the region that we're working with. All right, now we can define that in polar coordinates. All right. Again, we get this because this right here tells us, oh, we're doing, it's the negative semicircle, so this was really this side all the way over here. I just drew the circle because it gave us x squared plus y squared equals a squared. All right, so now let's go ahead and draw the region, because now we can go to polar coordinates. So our region is going to be for r and theta, our radius is 0 to a. Again, 0 to a because that's the length of our radius. And then our theta is going to be from, looks like pi over 2 to pi. And now we can go ahead and plug this into our double integral. So again, theta is on the outside, pi over 2 pi, and then our r is on the inside, so 0 to a. And now we're going to go ahead and substitute in. So x squared, y squared. X squared is going to be r squared cosine squared theta. Y squared is going to be r sine theta. And then on the outside of that is going to be r dr d theta. Alright, so let's go ahead and break up the integral because, again, they're just products of one another. I'm going to bring out cosine squared theta, sine squared theta, d theta, times the integral of from 0 to a. Have r squared times r, so r to the 4th dr. I'm going to integrate cosine squared theta sine theta. That's just really going to be negative 1/3 cosine cubed theta from pi over 2 to pi. And then I have r to the 4th, so that's going to be 1/5 r to the 5th. A to 0. Alright, so now plug in, if I do cosine of pi cubed, that's just going to give me negative 1. Negative 1 times negative 1/3 is just going to be 1/3. So I have 1/3 for the front, because cosine pi over 2 is 0. If I plug in a, I'm going to get a to the 5th over 5, and plug in 0, I get 0, so I get a to the 5th over 15. And that's the integral. Oops, wrong tool. Alright, now let's see the last one. Use polar coordinates to find the volume of the given solid bounded by the paraboloids z equals 3x squared plus 3y squared and z equals 4 minus x squared minus y squared. Alright, so I have two paraboloids, and I want to find the volume that's in between our two paraboloids. Alright, and the thing is, we don't know where they intersect. They could intersect over the xy plane, but not likely. And so we need to see the situation. Well, this paraboloid looks like it's opening upwards, while this paraboloid's opening downwards. I can tell because of the the values of the in front of the signs in front of your x squares and your y squares. All right, so this one is opening downward, and this one's opening upward. And so what I'm going to do is I'm going to try to find, so say here's the one that's opening downward, here's the one that's opening upward. I'm trying to find the volume of the inside of these two paraboloids. I'm trying to find that volume. And I noticed that they're going to have to intersect somewhere. All right, so that's the plane that I'm going to find my region over. All right, so let's go ahead and find the region. So I'm going to just have my plane. And now, where they intersect, that's going to be, the region that's going to be over this plane. And so I'm going to go ahead and solve for that. So I'm going to set the two equal to each other. So I get 3x squared plus 3y squared equals, because they're both equal to z, 4 minus x squared minus y squared. To find their intersection, I'm going to add x and y squared over to the left side. I get 4x squared plus 4y squared equals 4. 4's go away. I'm left with x squared plus y squared equals 1. So the intersection is going to be a circle with the radius of 1. All right? That is nice. Now, what I have to determine is, okay, how do I write my z? All right? So my f of xy is going to be, this, basically this shape. All right? It's that shape. So let me see if I can. So it's that shape, but I got to figure out how can I describe that surface. Well, it's not going to be too hard. The surface is just going to be whatever's on top minus whatever's on bottom. So the one that's on top is defined by the one that's facing downward. So we have 4 minus x squared minus y squared. All right, that's the one on top. And then we're going to, so then we have the one on bottom, so minus the one on the bottom, which is 3x squared minus 3y squared. So the top minus the bottom. And then that will give me, looks like 4 minus 4x squared minus 4y squared. We're going to pull out a 4, and I have, I'll do it this way. I don't need to pull out a 4. Minus 4x squared plus y squared. All right. Now I can change that to polar coordinates, and we'll do that. So now let's go ahead and do the integral, the region, and everything. So our region is going to be r theta. In terms of r theta, it's going to be r is going to be the radius, and we're going from 0 to 1. And then we have theta, which is going to be a full circle, so 0 to 2 pi. And then again, we're doing top minus bottom. And so our integral is going to go from 0 to 2 pi, 0 to 1. And then we have our function 4 minus 4. Instead of saying x squared plus y squared, we can say r squared. R dr d theta. Going to pull out the theta, and I'm going to multiply that by 4 r, going to forget to write the integral from 0 to 1, 4 minus, I'm sorry, I'll go ahead and distribute the r, so 4 minus 4r cubed dr. All right, integrate. So I have theta from 2 pi to 0, and then I'm going to have to r squared minus r to the 4th from 0 to 1, and I'm just going to get 2 pi for the front. 2 minus 1 minus 0. I'm just left with 2 pi. So that's the volume in between the two parabolas. So 2 pi units cubed. Alright, and that's it. So hopefully you found that wasn't that difficult, and this section wasn't that difficult.